We've referred to the idea of cell potential in a previous video, and today we're going to talk a little bit more about cell potential, how we know what it is, and how it can be used to make predictions about how electrochemical situations are going to behave. And then we're going to talk about a topic called electrolysis as well, which is where we force non-spontaneous redox reactions to occur. So if we set up this cell where we have copper on one side and copper sulfate, and zinc on the other side, and zinc sulfate, both 1 moles per liter concentrations. This is the reaction that will occur. The zinc will oxidize, and the copper will reduce. Why? Why does that happen? And if we hook this up to a voltmeter, we'll get a potential of 1.10 volts. Why is the potential 1.10 volts? These are questions that we need the answer to, so let's take a look at how to make those predictions. The energy that's available in a voltaic cell, or galvanic cell they're sometimes called, depends on the difference in the potential between the two half cells. So we picked a copper and a zinc, but we could have picked a copper and an iron cell, or a silver and a copper cell, or something like that. And all of those would have had what turns out to be predictable cell potentials, but it depends on the two half cells that you pick. To make predictions about which way the reaction is going to go, which direction the electrons are going to flow, and what gets oxidized and what gets reduced, we need a way to compare different half cells to each other before we put them together. So how we do that is we compare all half cells to a standard half cell and then keep track of those values. And then we can use that as a kind of a reference point and compare cells to each other based on how they behave when they're placed with this standard half cell. So the standard half cell is called the standard hydrogen electrode, or SHE for short. This is the setup. You have a piece of platinum, and we choose platinum because it's highly unreactive. And so it's just a conduit for electron flow. And then we put that piece of platinum submerged in a 1 molar acid solution. H3O plus concentration is 1 mole per liter. And then we pump into that half cell hydrogen gas at 1 atmosphere of pressure. So hydrogen bubbles stick to the platinum, and if we zoom in, we can see that there are hydronium ions in solution, and I've outlined these in pink to make them stand out from the water, which is what mostly is in there. There's a piece of platinum. You can see that those are the silvery atoms. And then there, in a little bubble there, there's some hydrogen molecules, H2 molecules. Now there's a reversible reaction up at the very top here, and it's proper to have this be reversible because this reaction can go either way. When the standard hydrogen electrode is functioning as a cathode, in other words it's a reduction, then the reaction is the way it is written above here. So electrons are going to come down through the platinum from the other half cell. They'll be added to hydrogen atoms on the hydronium ions, and they'll reduce, and those two hydrogen atoms will make water when they leave, and an H2 molecule. The opposite could also occur. Electrons could be drawn through the platinum out of the cell, and the reverse reaction would happen. So the reaction's going the other way now. So hydrogens are giving up those electrons, adding to water molecules, and making hydronium. So 2 water molecules became hydroniums because the hydrogen that was here isn't there anymore. It got oxidized. So it can oxidize or it can reduce depending on what's going on in the other half cell. So how this works is the reduction potential of the standard hydrogen electrode is defined as 0 volts. So it's just arbitrarily we say that that's 0 volts. So then what we do is we make a comparison by putting other half cells together with the SHE. So here's an example. If we put 1 molar zinc solution, zinc 2 solution, and a zinc electrode in a cell where the other side has the standard hydrogen electrode in it, we will get a potential reading of 0.76 volts. The cell potential is the sum of the reduction potential for the reduction that's occurring and the oxidation potential for the oxidation that's occurring. We are always making the assumption that the reduction is happening in the standard hydrogen half cell, and that is defined as 0. The cell potential according to the voltmeter, is 0.76 volts. So the oxidation potential here for zinc is 0.76 volts. Now the reason that we're assuming that zinc is being oxidized is because it's hooked up to the positive lead on the voltmeter, which means that's the electron absorbing, electron attracting lead. So we're assuming that the reaction that's taking place here is zinc is becoming zinc 2 plus and releasing 2 electrons. And because we're getting a positive potential here, that's actually what's going on. Now in the values that are tabulated in tables or online or in textbooks or things like that, reference tables, it's actually reductions that we are keeping the values for. We're typically recording values of standard reduction potential, which would be the reverse of this reaction. That would be where zinc 2 plus collects 2 electrons and reduces to zinc. If the oxidation potential is 0.76 volts, its reduction potential is the opposite of that. It's 0.76 volts negative. Here's a different half cell compared with the standard hydrogen electrode. Once again, because copper is hooked up to the positive voltmeter terminal, we're assuming that copper is oxidizing to Cu2 plus and giving up 2 electrons, and that the standard hydrogen cell is reducing. So the reduction potential for the standard hydrogen half cell is 0. The oxidation potential for copper is what's reading on the voltmeter, which is negative 0.34 volts. But remember, it's reduction potential that we put in these tables, so that would be positive 0.34 volts, because this is not the reaction that's happening. It's actually the reverse of this reaction, so we change the sign of reduction potential. So if a positive cell potential is measured, then the standard hydrogen electrode is actually undergoing reduction, and the other half cell is undergoing oxidation. That's what we saw when zinc was the half cell that was attached to the SHE. And the value of reduction potential is just the negative of the cell potential. If a negative cell potential is measured, which is what we saw here with copper, what's happening at the standard hydrogen electrode is an oxidation, and so what's going on at the other half cell is a reduction, and the value of the reduction potential is the positive of the cell potential. So just to review here, we have a positive voltage here, so that means the zinc is actually being oxidized, so its reduction potential is a negative of the value that's showing up on the voltmeter. But for this one, the copper is actually being reduced, so the reduction potential is the positive of the value that's showing up on the voltmeter. Now, you don't actually have to do this because people have done very careful measurements of standard reduction potentials, and they're all tabulated in tables that you can get on the internet or in reference books and things like that. A way of thinking about their usefulness is standard reduction potentials are a measure of the likeliness of a half cell to reduce. So let's put 3 things on here that we're familiar with. Copper has a reduction potential of positive 0.3 volts. Hydrogen ions, or hydronium ions in the model we were using, have a reduction potential of 0 volts, and that's by definition. Zinc has a reduction potential of negative 0.6 volts. And the reason for that is because zinc is more likely to oxidize than the hydrogen half cell. Copper has a positive reduction potential because it's more likely to reduce than the hydrogen half cell. So in general, the more positive the value of reduction potential, the more likely that half cell is to reduce. So now let's go back to our original question. Why is it that zinc oxidizes and copper reduces? Well, zinc has a reduction potential, standard reduction potential, of negative 0.76 volts. And copper has a standard reduction potential of positive 0.34 volts. Because copper has a more positive standard reduction potential, that means it's more likely to reduce. And because zinc has the less positive value of reduction potential, it's more likely to oxidize. So that's how we can make that decision. Why is the potential 1.10 volts? Well, the reason for that is because The cell potential, we're using standard cell potential here because molarities are all 1 molar. Cell potential is the sum of the reduction potential for the reduction that's going on and the oxidation potential for the oxidation that's going on. So the oxidation potential here is positive 0.76 volts because that's the opposite of the reduction potential for the zinc, which is actually oxidizing. And the reduction potential for copper is positive 0.34 volts. And so if we add these together, we get 1.10 volts. What's the direction of electron flow? Well, it goes from the anode where oxidation is occurring, that's the zinc, to the cathode where the electrons are needed. So that's left to the right on this half cell. Here's another example. You might want to stop the video here and try and figure this out. You'll need some information for Fe 2 plus 2 electrons reducing to Fe. The standard reduction potential is negative 0.44 volts. And for zinc 2 plus reducing to zinc, the standard reduction potential is minus 0.76 volts, as we saw before. Okay, what's the direction of electron flow here? Because zinc has the more negative reduction potential, it gets oxidized. And because iron has the more positive reduction potential, it gets reduced. So oxidation is occurring on the zinc side, reduction is occurring on the iron side, and so electrons are flowing in that direction. What's the value of cell potential? Well, zinc is actually being oxidized. So if we think about the fact that cell potential is oxidation potential plus reduction potential, the oxidation is at zinc, and so oxidation potential is positive 0.76 volts because it's going to be the negative of the reduction potential. And the reduction potential is negative 0.44 volts because the thing that actually gets reduced is the iron. And when we sum those together, we will get 0.32 volts. The cell potential in a voltaic cell is always going to be a positive number because these things are spontaneous. The bigger the cell potential, the more useful we could think about that cell in terms of its ability to provide energy through working by that electron flow. So you want a quite positive value of cell potential, but it's always going to be some positive value. Another thing that's useful about cell potential is it can predict the spontaneity of reactions that aren't a voltaic cell. And if you can figure out what must be the reduction, what must be the oxidation, and use the standard reduction and oxidation potentials, sum them up to get a cell potential, if that cell potential is greater than 0, that's a spontaneous reaction. If the cell potential is less than 0, that's a non-spontaneous reaction. Here's an example. If you put a piece of iron wire in 1 molar copper sulfate, does a reaction spontaneously occur? Well, if a reaction is going to occur, let's kind of draw a picture of this. Here's my piece of iron, and here's some copper 2 ions in solution. If a reaction is going to occur, copper is not going to oxidize. The copper is going to have to reduce. So we can think about copper 2 plus gaining 2 electrons and becoming copper. And iron can't reduce, it can only oxidize because metals don't make negative ions. So Fe will make Fe2 plus, let's say, and release 2 electrons. If we look up the reduction potential and then take its negative, we can get the oxidation potential for this oxidation. And the reduction potential is negative 0.44 volts, so this is positive 0.44 volts. And we know that this reduction potential is positive 0.34 volts. So when you sum those together, the standard cell potential is 0.34 volts plus 0.44 volts, which is 0.78 volts positive. It's a positive number, so that means this reaction will spontaneously occur, and copper will reduce and iron will oxidize. Here's another one. If we put, instead of iron, we put silver in the copper sulfate, was a reaction spontaneously going to occur? Well, here, the silver ions would have to be formed in oxidation. And the oxidation for silver, you can look up, the reduction potential is positive 2.87 volts, so the oxidation potential would be negative 2.87 volts. And so the cell potential is going to be oxidation potential, negative 2.87 volts, plus reduction potential, positive 0.44 volts. And that comes out to a negative 2.53 volts. So this is not going to spontaneously occur. That silver wire is just going to sit in there and not oxidize, and the copper will not reduce. Now let's talk about something called electrolysis. This is taking a non-spontaneous redox reaction and forcing it to occur by adding energy through working from an outside current source. So the question here is, what's the minimum external potential needed to cause this reaction to occur? Where copper is oxidizing and tin 2 is reducing. So in half reaction form, this is copper oxidizing to copper 2 plus and releasing 2 electrons. That oxidation potential is minus 0.34 because the reduction for the reverse reaction is positive 0.34 volts. We've seen that a few times. And then for tin 2 plus to collect 2 electrons and become tin, the reduction potential, we could look it up and we would find it's positive 0.14 volts. So the cell potential is minus 0.34 volts plus 0.14 volts, which is 0.20 volts, but it's negative. So this is a non-spontaneous reaction. Now, if we can provide a voltage that's greater than 0.20 volts, we can force this reaction to occur. Let's look at some more electrolysis situations. Let's say that we have molten Ki. So this is potassium iodide, salt that's been melted. And we stick 2 electrodes in there hooked up to a battery. What reaction will occur in this situation? Well, the potassium ions that are in there could only reduce to potassium. They're not going to oxidize more. The iodide ions that are in there are going to become I2. So that means 2I minus is going to become I2 and release those 2 electrons, which will then be used to reduce the potassiums. So the oxidation potential here is the opposite of the reduction potential for the reverse reaction, so that's a positive 0.53 volts. So the reaction that would happen is potassium ions plus iodide ions are going to make potassium and iodine in this reaction. Now that's not balanced. What's the cell potential? Well, it's the oxidation potential of positive 0.3 volts plus the reduction potential of negative 2.93 volts. And if you add that together, you find out that the cell potential is minus 2.40 volts. The next question here is the 1.5 volt battery sufficient? Well, no. This reaction will only happen if you have an external voltage applied that's greater than 2.40 volts. So that would not work out. Here's another one. Instead of melted liquid Ki, we have a solution of potassium iodide, 1 molar solution. What reaction will occur here? Well, now we have some options. Potassium could reduce, and that would be the reduction potential, but you also have water in the solution, and that could reduce. So we have a choice between these two. Of those two, this is the most positive reduction potential. So the reduction is going to be H2O plus 2 electrons makes H2 plus 2OH minus. Now, in addition to iodide ions, which we had in the molten Ki, we could also have water oxidize. So if that was the case, the oxidation potential would be negative 1.23 volts if this reaction went in reverse and oxidized. So it's just the minus of that, compared with positive 0.53 volts for the reverse of that, for the oxidation of iodide. This is the most positive oxidation potential of the two, and so that means the iodine ions are going to oxidize to I2s and release 2 electrons. So the overall reaction is going to be H2O plus 2I minus will make H2 plus I2 plus 2OH minus.